Hello, yeah, it's 7. We'll wait for a few more minutes and then start. Yeah, hello everyone. I'm Suchit Prabhu, a PhD scholar at IIT Delhi, working with Sumit Agarwal and Manik Verma on extreme classification. Okay, and so let us begin. Lalita had a doubt.
Yeah. Hello, sir.
I,
This earlier also this doubt was there. It was not clarified, and I checked the answer sheet. That is not. I mean the answer key. That with that also I have this doubt. I asked in the forum also. Still, it is unclear. This is quiz of week 2, question 10.
okay, so
Can you open that?
yeah, Now let me share my screen.
Yeah.
This question, right?
Yes, yes.
Okay. Suppose that we implement the XOR Boolean function using the network below. Consider the statement that a hidden layer with two neurons is suffice to implement XOR. The statement is true. Fine.
First of all, inside the neuron, what is written? Uh, that is unclear. What do you
Okay.
mean by one inside that neuron? Does it mean, I mean, very ambiguous. It's like, does it mean that it will get fired with one output?
Okay. So
Still, if I try to work it out, it is not coming.
so I think these are the weights W1
No,
and W.
the weights are marked as like minus red and blue. So it's all red, blue, red, blue, red, blue. For all the neurons, the weight are -1, +1. And that's what the legend
Okay.
says. Yeah.
Okay, fine. So yeah, we should be able to like implement, right, with one layer. Okay, so what does this
If
mean?
you can show me the working, I've been struggling with this. I checked whether it's correct or not. I mean, the picture is correct. Diagram is there any issue with the diagram?
Okay, I think
For the truth
let
table,
me
if I say,
yeah, so for 0, 0,
for 0,
uh,
0, the answer will be like minus
0.
2. Minus
Ha,
2
-2,
biases.
but okay. Yeah, -2.
Yeah,
And
but then
for
it will not get fired. Yes.
okay,
But this says that it will get, for the first one, will get fired. I don't know how. Second one also, if I see,
okay. So suppose we have 1, 0 here. It will not get fired, right?
yeah, +1 and -1, and
Okay, so let me check
it will.
the
Yeah.
notes.
I mean, actually, I mean, you can revert
It's
later
not
also if it is to take time. I
okay.
somehow felt like that.
It should not take time. Like, let me check the lecture slides and so this is from week 2, right?
Yeah, lecture, the diagram was correct in the lecture.
So this was in the beginning, right?
Yeah, yeah, beginning, the first, uh,
Okay, over here.
must be the second slide or something.
Sigmoid
That
starts with sigma.
multiple, this is a single, no? When the multiples.
Okay.
Yeah, yeah, yeah. It's interesting. We went ahead. I can tell you, I will also open.
Here, it's not here also.
Yeah. It's 30. Oh, it's there. It's there. It's
And this is,
there. Mm,
I think it's in some other slide, sigmoid gradient descent and representation power. So I don't think this is it.
it's week. It's week two.
Week two or week
Week two.
one? So
Week two.
I,
Week two. Week one did not have multiple neuron. It's week two. I mean, I have the notes with me, so date wise. I'll open.
yeah, I think it's here. Let me download this.
I've downloaded it.
Okay, it was this, right?
Mm,
It's the
Yeah,
same
this one.
question from here.
Yes. Yeah, this one.
Mhm. Okay, let's see. So the diagram is incorrect, right? So
Yeah. So I asked just
in the
last week
question.
again. I asked the TA in the group that is this there is a mismatch in the diagram and the description.
Mhm.
In this diagram, if you do here, I think 0 0 instead of 0 0, it is false. So -1 -1.
Mhm. So what are they trying to model here? I don't remember what is happening here.
So I just wanted a clarity whether that diagram question is wrong. The diagram is wrong for the question. At that time also we tried asking, but there was no response.
Okay. So again here, okay, it's the same question. Here also they are trying to model exam. It's exactly the
See
same question,
here,
right?
yeah. So now if you see the first neuron, if you see the weights for the first neuron is both red, and the weights for the last neuron are both blue.
Mhm.
That's why it is able to get that.
Yeah,
And here it is all are plus minus plus minus
plus
plus
minus,
minus.
yeah.
Yeah. So there
So the
is,
diagram is incorrect, but
but there no, but TA is not accepting that.
okay.
What is wrong in that? Or is it like not able to, I'm not able to understand. Same thing comes in the exam.
So see,
That's why I wanted that clarity on that.
okay.
Is it something that I'm not getting it?
It's exactly the same, right? Same
Yeah,
question.
correct.
Yeah, so it's so the diagram is incorrect.
In
Okay.
one of
But
the
if you consider just
Saturday
the
lecture also, yeah, that also if I consider, I mean, even if I consider minus minus also or 0 0,
mm,
it is not working. And then I saw the description when that answer key, it looks like it is answer key is different and the diagram is different.
okay, fine.
I got a response saying that please check it again, it is correct only.
Okay, so let me, yeah,
You can check and
yeah,
is there a way to get it checked? Because in the forum they clearly said no, it is correct, but it is not correct.
okay, fine. So, yeah, so I'll go through the question again and
Yeah,
look at the
yeah,
solution now. So I'll let you know, okay?
yeah. Sure. Thank you.
Yeah, I'll answer you in the forum. I'll answer in the forum, okay?
Okay. Thank you.
Divesh, okay.
Yeah.
Hmm, fine. Yeah, any other questions or doubt? Okay, so last week we dealt with images, and this week it was about text. So how to uh, text or sequential data. Okay, so we saw sequence learning problem. Okay, and then so what how we can use RNNs uh, to model or to deal with the sequential data. Okay, so we were primarily dealing with text. Okay, and previous model could be used, but there are certain characteristic like the input size can vary. So for modeling those problems, recurrent uh, those problems can be modeled properly using RNNs. Okay, and then we saw how we can train RNN uh, using backpropagation through time. Okay, and saw the problem of exploding and vanishing gradients. Okay, after that, selective read write, and through that we yeah, then covered LSTM, gated uh, gated recurrent unit, GRU, and then yeah. So these were the things that we saw this week. Okay. So let us go through each of this topic in detail now and solve a few questions. So before this, let's start with the question only. Okay, so here's the first question. So what is the basic concept of RNN? We use a loop between inputs and outputs in order to achieve better prediction. Use a recurrent feature from dataset to find best answer. Use loops between most important features to predict next output. Use previous input to find the next output according to the training set. So which one is correct among these
Fourth
four
one.
options? Yeah. So the previous input. Yeah. So this is correct answer. The fourth one. Okay. So select the correct statement about GRUs. GRU have fewer parameters compared to LSTM. GRUs use a single gate to control both input and forget mechanisms. GRU are less effective than LSTM in handling long-term dependency. GRU are a type of feed-forward neural net.
One is correct, two is correct, three is also correct.
Okay, so why is the first option correct? GRUs have fewer parameters compared to
Because
LSTM.
it is because of the second thing only. It is using a single gate.
Yeah, single gate instead of using. input and forget get, right?
Yeah.
So that's why it'll have fewer number of parameters because we'll need extra parameters to model the gates. So okay, so the first is correct. Yeah. Third is incorrect. Is less effective than handling long-term dependency. So it can't be, we can't comment about this. Could be that in some data set GRU perform well than LSTM and vice versa.
Mhm.
Yeah. And the third option is again incorrect.
Yeah.
And so, yeah, the statement that LSTM and GRU solve both the problem of vanishing and exploding gradient in RNN is
They solve only vanishing, both of them.
yeah. So this is false. Okay, so why are these networks able to handle vanishing gradients and not exploding gradients? It is because the way the network is formulated, the way we calculate a cell state is we apply forget gate to the previous state, and then uh, there is input gate connected to the intermediate state. So because of this addition, yeah, so it's like a skip connection. And so this addition allows the gradients to pass. So that's why the vanishing gradient is solved. Okay, and exploding gradient because it's still a RNN, right? So the issue of exploding gradient doesn't go away. So we'll see in detail why that is the case. It was covered in lecture as well because we could find a path. Okay, so to prove that vanishing gradient, we just have to find a single path so that gradient can be passed. But for exploding gradient, we have to make sure that through all the paths, the gradient doesn't increase. Okay, so yeah, so this was covered in the lecture. Okay, so we'll go through it again when we go through the slides. And but the answer is false. Yeah, so what is the role of forget gate in an LSTM network? To determine how much of the current input should be added to the cell state. Okay, to determine how much of the previous time step cell should be retained, and to determine how much of the current
Second one, to
cells should
determine
be
how much
uploaded.
it should retain.
Yeah. Yeah. So if you look at the equation, so the role of forget gate, right? So forget gate is being applied in the states part, the second equation, and it's being applied to the previous state. How much of it should be retained in the current cell state? So the second option is correct. Okay. Now arrange the following sequence in order they are performed by LSTM at time step t. Selective read, selective write, and selective forget. Okay, so here are the
Second one,
equations. You
Third, third,
can
third.
could you explain like why do you think it's the answer? So here are the equation from the slides. So what is happening in each of this? The first one. First, second, and third. So you're taking the previous output here, okay, in the first equation, and then yeah, so finding out what is important here and coming up with this intermediate representation, right? So this is like you're reading from the output. So this is read operation, okay? And based on the previous and this intermediate, you're applying these two gates. So yeah, you're forgetting and then uh, this input gate and coming up with this current one, and the finally based on this current state, you're giving an output. So this is like write operation. So it's read, forget, and write. Forget and write. So the third option. So is this clear?
Yes, yes.
Fine. So we are given a RNN where max eigenvalue of weight matrix is zero point 0.9. The activation function used in RNN is logistic or sigmoid. What can we say about yeah, this delta? This partial derivative of cell state 20 by cell state 1. Value of delta is close to 0. It's very high. Is 3.5 insufficient information to say anything? So the answer is it is close to 0. A, because this value, this gradient value is proportional to lambda times the some constant times the eigenvalue raised to the power, right? So it will be zero point 0.9. So if the value lambda is if the eigenvalue is less than 1, then we'll have that vanishing gradient effect. So it'll be close to 1, close to 0. Sorry, so first option is correct. What is the objective function in the RNN? Cross entropy, sum of cross entropy, squared error, accuracy. This question is a bit this question is a bit ambiguous. It depends on the task that you are performing. Okay. But in the lecture, I think they gave an example of language modeling. So there will use cross entropy, but depends on their task. So what are your thoughts on this? And moving on. The answer is cross entropy. Which of the following is a limitation of traditional feed-forward neural networks in handling sequential data? They can only process fixed length input sequence. They are highly optimizable using gradient descent. They can't model temporal dependency between sequential data. All of these.
See, they
Hmm?
can't handle temporal data.
Yeah, can't handle temporal data. Also, they can only process fixed length input sequence. That is also a limitation.
Okay.
The answer is A and C. Fine. Uh, moving on. Which of the following technique can be used to address the exploding gradient problem in RNN? So one way to deal with the vanishing gradient is to use LSTM or GRUs. Okay, but yeah, they still don't solve the exploding gradient problem. But this problem is easier to handle. So what is the technique?
Gradient clip.
Okay, could you?
Gradient clipping.
Yeah. So what happens in gradient clipping?
We are clipping the gradients, so the value will not go beyond that. It will not
Okay.
explode.
Okay. So if it goes above threshold, you will replace it by that threshold.
Yeah.
That is what is happening. So what type of neural network is best suited for processing sequential data? Convolution neural network, recurrent neural network, fully connected neural network, deep
RNN.
belief network. Yeah, RNN. And so any questions regarding any doubt, any other questions? Anyone? Fine. So okay. So before going through the notes for this week, what we'll do is because this week it was all how to deal with text, right? And till now, whatever training we did, okay, so we had used we had used PyTorch, the PyTorch library, and written the training loop and all from scratch. We didn't use any high level library on top, which is written on top of uh, PyTorch. So what we'll do is we'll look at this example from Kaggle here, okay, and we'll try to solve this. And for this, we'll be using so this is a NLP task, okay. We'll go through what the task is, but we'll be using Hugging Face library and train a classifier. Okay. So so on Kaggle, so Kaggle is a platform which hosts machine learning competition. So anyone can participate. So this is a very old competition. So the task is yeah. So you want, so there are two pieces of text given, and you want to find how similar those two texts are. So that is a task. So in this competition, you will train your model on novel semantic similarity dataset to extract relevant information by matching key phrases in the patent document. Okay. So yeah, so the task is semantic similarity between two pieces of text. Okay. And the evaluation will be done on so the dataset has a pair of text as well as a score for that text. So what we'll do is we'll train a classifier, and then whatever probability our classifier assigns will consider that as the score for the similarity, and then the final evaluation will be based on this Pearson correlation. So how these scores are correlated to what we get as output. So what our model predicts. Yes, you can read about the Pearson's correlation coefficient here. Okay. So this is a formula for computing it. Okay, so yeah, so you can so in this data tab, you'll find out description of the data. Okay, so there is anchor text and this target text, target frame. So we have to find similarity between those two texts, and this is the score that they have given. This is between 0 and 1. Okay, and there are three files here: train.csv, test.csv, and different columns which are present. Okay, so we yeah. So you want to use these two and come with a score. Okay. So is the task clear to everyone? So given two texts, text T1 and T2 are so we want to predict how similar they are, and our score should be between 0 and 1. So we could treat the output during modeling this as predicting probability of the two classes. Okay, we're just predicting a probability score. Fine. We'll see. So here is the code to download the dataset. Okay, from Kaggle directly. So I already done that. Okay, so these are the three files. So uh, so as mentioned there on the computation page, so it has ID. This is the anchor text. Okay, the target text between which we want to find the similarity score, and this is the target similarity score that we want to achieve. Okay. Now this uh, so we have used pandas here. So df is a data frame. Okay. So if you look at its type, it's a pandas data frame. And pandas is a library to deal with tabular data like this. Okay, so this has a member function which will uh, list some properties of that data frame for each of the column. Okay. So it has listed the count, number of unique entries in the column. Okay, yeah, top entry as well as frequency, most frequent of the top entry, frequency of the top entry. Yeah, so before doing anything, it's good to see what is there in the data set and look at its statistics. Okay, now what we'll be doing here in this assignment in this notebook. So we'll be using uh, DBERTA model. So it's a transformer based model. It's a encoder only model. So so what we'll do is so we'll concatenate both the text together. Okay, and then so this is the prompt to the transformer model. So we'll concatenate the text, pass it through the transformer, and then after that we'll get a so we'll have a classification head on top of it, and then use that to score. Uh, yeah, over it. We'll use a cross entropy loss and train the model. So instead of using so it's a classification task. So whatever we get as output, so we there is a relinear after that, and then uh, we'll train it using uh, cross entropy loss. Yeah, the training is similar to how we train other classification model like CNN. Okay, so yeah, so the input to the model will be in this field of the data frame, and so this is how the input looks like. So you have concatenated all the information. Fine. Okay. So now, so you want to create a so from this data frame, you want to create a data set and then data load and pass it through the model. Okay. So we are using this library called dataset from Hugging Face, and yeah, so this creates a data set. So yeah, so we can index into it directly, and we'll get a data point which will be fed into the model. Right? Yeah, so till now we had ourselves like written a class to train a model, but now we'll be using this transformer library and yeah, and directly load a model from it. Okay, because this is a uh, NLP task, so the text has to be converted into tokens, and then so there's a tokenization. So we'll have to tokenize the text, and then the numbers would be so yeah. So we'll have to convert these text into numbers and then feed it into the model. So for that, we'll need a tokenizer. Okay, so and because we are using a pre-trained model like Deberta, we'll have to use the same tokenization that this model use for its pre-training. Okay, so here, yeah, so this is the model name, and we are downloading the yeah. So we'll loading the tokenizer over here. So yeah, so we had done something similar when we were doing character level language modeling. There we had built the uh, vocabulary and all ourselves for the character. But here, because we are using a pre-trained model, we'll have to use its same use its tokenizer. Okay, and this is what this function calls the tokenizer and tokenizes it. Okay. So this is where the tokenization is happening. So we have loaded the tokenizer and we are calling it on the input here to tokenize it. Okay, so this will add another column into the data frame. So if you look at the data frame now, sorry, data set. So it has these columns input. So after this, it'll add the attention mask, and there'll be one input IDs. So those two columns will be added. Okay, so we have the tokenized data set. Okay, so yeah, so there is input IDs. Uh, this is the token type and the attention mask. Okay, so yeah, so this is the tokenized text which we have. So the text, this text over here in the input field is converted into numbers, and that is present in this input IDs field. Okay. Now this token type is something to do with the BERT model, the way it was pre-trained. So the BERT model is trained on two tasks. One is on masked language modeling, and the other one is next sentence prediction. So for that, this token type is required. But yeah, so for our task, we don't have to. This will be all zeros every time. Okay, and then attention mask is there because so it'll be same as the size of the input. Okay. Yeah, same as the size of the input. And when we create a batch, uh, so we'll have sequences of different sizes. So at that time we'll have to pad this with zeros. Okay, so that yeah, so that the network does not attend to the padding tokens. Okay. So these are the input IDs. If you look at the length of this, it will be same as the attention mask. Yeah. And the size, each sequence will have different size. So before passing to the model, so model will take like a batch of data at a time. So so what we'll have to do is so before passing to the model, uh, we'll have to somehow pad like all the sequence should have like the same length. So we'll have to pad. Uh, we'll have to take the maximum data point with the maximum sequence in the batch, and then pad rest of the data points in the batch uh, accordingly using the pad token. And this has something to do with the Hugging Face library. Okay, the next step. So our data set had like these columns, and our target was this score, right? Now in the Hugging Face library, the target the name of the column of the target should be label. Okay, so that's why we are renaming this score as label, because that's what the library expects. Because this is our target, so this is what we want to achieve. Given to target and the context, we want to predict this score. This will be our labels. Okay, so we have just renamed the column so that we can use the library. So the score has now changed to labels. Okay, I will create a testing split. Okay, so we have this data set, and then the there's eval set as well. Which will finally, so once you have trained the model, we'll use that to eval. So there's a test set over here, which I'm calling eval df. So similarly, we'll have to do the same processing that we did for training data to evaluation data frame as well. Okay. Yeah, so we are loading it as a data frame. Okay. Yeah, so the input is formatted in the same format. Okay, so we'll concatenate the two texts together and we'll feed it into the network. So that's why the context column and this target column, so we are, yeah. So you're concatenating everything together and then creating a single input and then passing it to the tokenization function to get the final data set. Okay, so this also has the input IDs, which are the tokens which will be feeding into the model, the token type and the attention mask. So these are the three inputs that the uh, that our model expects. Okay. So what we have done till now is so we have read the data set, okay, formatted it. Okay, so this is a decision that we want to take, what should be the input to the model. And we have decided to get a score for that two pieces of text, we'll concatenate them together, pass it through the neural model, and then get a single score. So that's how we have model. Okay. So there are other ways as well. So what other thing that we could have done is we could have sent these two texts independently through the transform model. Okay, and then instead of getting a final score as output, we could have gotten the embedding representation of those two texts. Okay, and then could have used there are loss function like cross entropy loss. Okay, so what it does is so texts which are similar, it'll try to get its representation closer together, and those which are dissimilar, uh, its vector representation will try to pull them apart. So there are loss functions like this. Okay, and yeah, we could have learned a dual encoder. So these uh, models are called dual encoder, and then finally the similarity score could just be cosine similarity between the two vectors. So that is also a way to model, and because we are inputting like concatenating this, so these models are called cross encoders because we are concatenating both the target and the context together and coming with a single score. Okay, so this is the design choice that we yeah, so this is a design choice, and there are various way to deal with this, and then yeah. So once this is done, we'll tokenize, get the tokens, and then finally load the model and train it. So let's do that now. So so these are various training arguments. So batch size is 128. The learning rate is 80 minus 5. Okay, and we'll train it for 4 epochs. Okay, so these are the various parameters that the library allows us to use. Okay, so per device, what the batch size should be, then learning rate, warm up ratio, the learning scheduler that you want to use, and this is if you want to do operation in FP16. Okay, so how many bit floating point integer should we use? So this if you use this 16 bit floating point 16, then it'll take uh, less memory. So depending on how much RAM you have in the GPU, you can choose this. Okay, and this is weight decay. Weight decay is L2 regularization. It's called weight decay over here. Okay, and so here we are uh, loading the model, which is a debutta. So we're loading this debutta model. Okay, so what this does is uh, so all the models are present in the Hugging Face repo. So when we call this, give it this model name, it will download a pre-trained model from the internet. Okay, pre-trained model, and then yeah, and they specify a number of labels. So yeah, because we just want a single score. We just have one label. Fine. So this is the correlation. So this is the metric that we will be using. Uh, yeah. So you're using NumPy and directly using a function called to compute this Pearson correlation metric, which takes as input the predicted and the final score. Okay, so this is the trainer that we define. So trainer, so if you look at the code inside, trainer has the training loop. Okay, so it takes model all the training arguments, the training data set as well as the evaluation data set, the tokenizer, and then yeah, the coefficient. And if we call train, it will start training the model. Yeah, so dbeta is I think it's a very small model. It just has 130 around 130 million parameters. So yeah, so you should be able to train it on Colab itself, and it won't take much time. So any questions, anyone regarding this? So what we have done today is yeah, so we have taken a real world problem and from Kaggle and trying to solve it. And instead of implementing all this training loop ourselves, what we have done is we have used a Hugging Face, a high level library which is built on PyTorch, and then try to train a model. So any questions regarding this? Anyone?
No, sir, thank you.
Hmm?
No questions.
Okay, so see. So you can see the validation loss is decreasing and our score is increasing. So the score higher the score, the better is our performance. So I'll share this notebook. So yeah, so you can use this as a reference code and then solve other problems as well, other classification task. So you're just yeah, text classification tasks. So you're just we just had one label here. Okay, so you could try different as well. So data set which has like around 1,000 labels. So my research work is related to this only classification, but extreme classification. So when the number of labels are very extreme, like it's in millions or uh, it's in billions. So in that case, we can't like learn a cross encoder like this. Okay, because the final layer, the number of parameters in the final layer explodes because yeah, so it'll be million across the dimension, hidden dimension. So yeah, so there are techniques, other techniques which could be used in that case. So we have completed 4 epochs now. So this predict function will do the evaluation for us. So this is also again from the Hugging Face. And yeah. So here are the predictions from the model. So this could be used as scores. Okay, so but you can see there are negative values as well. And what the what it expects in the dataset is the score should be between 0 and 1. Okay. So for now, what we'll do is if you want to submit it to Kaggle, okay, so we can submit it as well uh, and see where we stand. So what one thing we can do is now we can just clip the values between 0 and so negative values would be 0. Okay. Yeah. So there are other ways. What we could have done is because we know the value is between 0 and 1, so the final score that we get, we could have passed it through a sigmoid function so that the value is between 0 and then on top of that trained our model. Yeah, so what we have done is we have trained a model and yeah, we have a score of 0.93. So let's see where we stand on the leaderboard. So this week, so the data set which they have used, so they have used a separate private data set, but yeah, so we have our evaluation on the validation set for the data set which they gave. If we see, yeah, so we just trained it for 4 epochs, but yeah, with that, let's see where we are. 83. Yeah, so we are in like top 1000 and top 1500. Yeah, so any questions regarding this? So I'll be sharing this notebook so you can run it on your own. Uh, any questions or doubts? If I, yeah, let's take a break now for 5 minutes and then we'll continue again from here. Yeah, so now, so let us like revise whatever was done this week, and then yeah, come back to so then again come back to coding. So what we'll do is after that, yeah, so we'll train a sentiment analysis model. Okay, so for that we'll use LSTM. Okay, but we'll not be using any library here. Okay, so we'll be writing out the class. Okay, yeah. So this will be done on top of. So we have written the training loop here as well, the evaluation loop. So we'll be using PyTorch here again. Okay. So but before that, yeah, let's revise whatever was covered. Okay. So so we started with sequence learning problems with this week. Okay. Now the problems that we have seen till now, for example, in CNN, we dealt with like a fixed input, like image. Okay, so images could be obviously a different sizes, but before feeding into the model, we resized all the images and then fed it into the convolution neural network. But there are tasks, sequential tasks, where the input could be of different sizes. Okay, for example, if you want to do sentiment analysis, okay, so given a text, so given a review, you want to yeah, IMDb review rating if you want to do. So the reviews could be of for each reviewer could give like a review of different length, right? So to account, so normal, so the new also the language modeling task that we saw, where the task is given previous input, predict the next word. Okay, there also what we had done is we had fixed the size of the input. Okay, so we were just looking at two input and or two or three input and based on that predicting the next word. But what we could have done is yeah, so we could have accommodated uh, different sizes as well. Uh, so that could be done using LSTMs or a recurrent neural network. Okay, so this is the language modeling task that I was talking about. So two words were taken as input and yeah. But yeah, so using LSTM, this input could be the context could be of varying different sizes that could be accommodated using a recurrent neural network. Okay, so this is the classification task that we saw. So all here, so in all this task, the input was fixed. So yeah, so we want something like this where for different we should be able to process input of different lengths. Okay. So this is the POS task that we saw, and the sentiment analysis. The review could be of different. The review text, the size could be of different sizes. Okay. So this, yeah. So all this task could be. So the approach which we saw was recurrent neural network. Okay. So these UV weights are shared for different along the time step for different time step. This UNV UNV weights are shared. So this is how we are going to model it. Okay, so there'll be xi is the input. So based on the input, we'll multiply it with a matrix, and this Si would be our cell state. Okay, and this cell state, yeah. So this is one way of doing this. This cell state can then be fed into the next time step, so that we have that dependency uh, captured for a different time step. Okay, and then the cell state is then finally used to predict the final output for this given step. So this is how we are trying to model. So yeah. So we want to capture the dependency, what our solution was, will share the weights. Okay, yeah. And this previous, so this is the equation of the recurrent neural network. Okay, the vanilla RNN equation. Okay, so the current cell state is computed as a function of this xi and the previous cell state. And U, V, and W are the parameters of the network, and it's shared across the time steps. Okay, so W, B, and C are parameters, and X, I, and these are the input to the model. And based on this, we'll predict the output. So output depends on the task we are trying to solve. And it's recurrent because yeah, so you're feeding in the we are feeding in the previous cell state to the current state. Now let's see how to train this model. So we have defined so this is the equation. So with this we have defined our neural network. So if we implement this with code, we'll have to write a for loop. Now let's see how we'll do that. So to train the network, we'll need gradients, right? So because we'll be using optimization techniques that we saw like ADAM or gradient based optimization technique. So we'll have to compute gradients with respect to the loss function. Now let's see. So because of this recurrent nature, yeah, let's see how the gradients will flow. Okay, so these are the dimensions. So input X is n dimension, then cell state has dimension D. The output is R raised to K, depending on number of classes we have. Okay, so U will be multiplied by Xi, so it's Rn cross D. And similarly, V, which is output, so it'll be multiplied uh, by the cell state Si. So it should be D cross K. K classes because we are modeling so the final task here would be classification, so that's why it'll be R raised to K. And W would be D cross D because W gets multiplied with the previous time steps cell state. And we'll be training this using backpropagation again. Okay. Now, yeah. So this is the loss function. Okay, cross entropy loss. Now finding the gradient with respect to this V vector is easy because we'll just accumulate across all the different loss at each time step. Okay, so that's why there is this summation. Okay. The interesting part is when we go to compute this gradient of this W or U. Okay. Yeah, so what we'll do now is we'll just consider one loss function L4 and we'll compute like gradient of yeah derivative of W with respect to L4, and we'll get this graph structure where L4 is dependent on S4, the cell state S4. Okay, but S4 is in turn dependent on S3 and W. Okay, then again S3 is dependent on S2 and W. So when we do backpropagation, we'll have to like accumulate all the gradients which come into W through all of these paths, all of these four paths. And yeah, so for this we'll just apply the normal chain rule. And finally, so the way to come with a very precise equation. So in the lecture, they had divided this into explicit and implicit gradients, but all they are doing is applying the product rule and then followed by chain rule. Okay. Yeah, so now what they are considering is forget that this non-linearity is present. So yeah, so suppose we want to find this gradient of derivative of W with respect to S4. Okay, so here we have two. So they are product of two terms, right? A and B. So we'll apply that product rule and we'll get this these two terms over here. So in the first one, what you're assuming is yeah, so S4 is like uh, a constant, so it is not dependent on W, and will compute the gradient with respect to W. And then in the second part, yeah, so we'll find derivative with respect to S4. So W times S4. So yeah, so this is just a equation of the product rule. Okay, and then we'll keep on expanding this, again applying the same chain rule and then the product rule. So again we are expanding this, and here we have the product rule, and we'll continue this till the start state, and this is what we'll end up with. Yeah, so if you, this is very easy to understand if you do it on a pen on paper. It's just product rule and then chain rule. So any questions regarding this? Any doubt or question? And you just have to, so yeah, be aware of this notation, okay? But if you open it up, it is just product rule for then a chain rule. Okay, and then finally, what we get is this this equation for finding the gradients, and we'll have to do this for all the loss functions. So yeah, so we'll have to do it for different time step, and this is what we get as a final equation of the gradients for computing the gradients. Any questions regarding this? And moving on. Yeah, so yeah, we'll look at the issue of exploding and vanishing gradient. Now the main issue why we have this issue is because we have this repeated multiplication of uh, the same weight. Okay, because we are doing a parameter, we are sharing the parameter across different time step, and we are continuously multiplying by the same matrix W. The so that's why it could be that leads to this vanishing and exploding gradients. Okay, so there are various ways of handling this. One is gradient clipping, or uh, don't do backpropagation from time t to the initial time. Okay, so we can say that while computing this from t to some time step k, t minus k will do this for computing gradient of w. So yeah, so that could be also done. Okay. Now here in this uh, these slides, we'll see the mathematical uh, formulas which uh, uh, which precisely formulates the vanishing and exploding gradient issue. Okay, so it's because of this repeated multiplication. So as if we look at this product of these derivatives, okay, so we'll look at just one term, and that gradient would be, because you're multiplying with by w, it will be a product of w. Okay, it's a diagonal triangle. So yeah, so it's because of this w that causes that issue. Now suppose the eigenvalue is greater than 1, so this repeated multiplication would uh, so in the forward path as well, it will increase the size of the vector. Suppose there is a vector x, okay, and suppose this eigenvalue is greater than 1. So after repeated multiplication, like w uh, w raised to k times x, so that vector would, the length of that vector would keep on increasing. So similar thing happens during backpropagation. So this has been, yeah. So the first term is a nonlinearity, and its gradient is bounded in case of logistic sigmoid function and tan h. So for sigmoid function it's 1 by 4, and for tan h it's 1. So we can write this gradient as gamma times lambda, where lambda is the eigenvalue of this w matrix. And yeah, so this is what we get. It's precisely because of this weight sharing that we see this vanishing exploding gradient problem. Okay, and when this value is less than 1, we'll observe vanishing gradients, and when it's greater than 1, we'll face exploding gradient problem. So this is like the mathematical formulation of it. But the idea is we are doing repeated multiplication with the same matrix. That leads to this problem. And any questions regarding this? Any doubts? Fine, moving on. Yeah, so one is to use truncated backpropagation. So we'll not go from t to the starting time. We'll just accumulate the gradients till some k minus t steps from t. Or we'll use gradient clipping. So that could also be used to solve this issue. Okay, now so here we look at the actual gradient computation. Okay, I'll not go through this in detail. So there is one. So the last term over here is a tensor. So in the slides, we see how gradient for that tensor could be computed. Okay, and this gradient would be sparse. If you go through the derivation, you'll see that most of the entries would be 0. Okay, so yeah, so this is what was covered in the first part, and then after that, to deal with this vanishing gradient problem. So this LSTM architecture was introduced. So basically, we saw how this analogy of selective read, write, and forget was introduced. Okay, so yeah, so these ideas were incorporated and to come with the LSTM architecture. Okay, this is an analogy in the lecture. Okay, so we'll go through what happens in LSTM and GRU. So there are various formulation of LSTM. We'll see what happens over here. Okay, yeah. So ideally, what we want is forget the information added by, yeah. So you want to forget some information, selectively read information from the previous time step. So we want this precise control over what is, so if we see the self state as a memory, we want exact like, precise control of what could be written or read from it. Okay, and this is achieved by like learning, so by adding extra parameters to the network and learning these gates. Okay, so this is the wish list. selectively write, selectively read, and selectively forget to ensure that finite sized state vector is used effectively. Okay. So yeah, so the input, so what we want is we want to use the previous, just like in RNNs, use the previous cell state, which is ST minus 1, and this current input XT. And finally, we want to come with this XT as output, the next cell state. Okay. But yeah, so we don't want to use like the previous equation that we used. We want to do selective operations here. Okay. So let's see. So what we'll do is for selective, right? So what we'll do is we'll learn this OT minus 1, which is the output gate. So equation of that is uh, given by this. Okay, so we'll be learning. So this WO, UO, and BO are extra parameters to learn this OT. Okay, so this again is passed through the sigmoid. Okay, so you can think of this like a switch. Okay, a soft switch, and it decides. Suppose if we had a hard threshold here, so it will just output a binary string of zeros and ones, which decides uh, which of the uh, which of the values from the previous state, okay, should be written out into the output state. Okay, so because we want the network to be differentiable, we'll be using a sigmoid function. Okay, and all these parameters will be learned. Okay, yeah, to simulate this switch like behavior, so what we'll do is we'll just come up with this soft values and then multiply with this with the previous states. And yeah, so this what HT minus 1 is the output that we get. And yeah, so we'll be using this then to compute the temporary okay. Yeah, so this is called selective right. And then selective read is we'll use this HT that we got the output of the previous time step. We'll use that and come up with this intermediate representation of the cell state. Okay, this is again the equation that we saw previously for RNN. Okay, but in addition to that, okay, so we'll learn a gate again over here to decide what we should read from this, and then we'll combine this with the cell state of the previous as well. So this is called selective read. Okay, so come with temporary cell state and then decide depending on the gate what to read from it. And then there is a forget gate as well because we want to combine this the temporary cell state that we got with the previous state. We'll not combine it directly. We'll have another gate over here which tells us what to forget from the previous cell state. And that will and we'll take a combination of this temporary and previous cell to come with this current cell state. Okay, so this is the equation of the forget gate, and then yeah. So this is finally the cell state is given by this equation. So here are all the equations. So we have three gates. One is output, input, and forget gate. And these are the equations. Okay, so what we are doing here is yeah, selective read because from the previous state's output, we are trying to read and come with this temporary cell state. Okay. And then using this temporary cell state and the uh, previous state. So we're trying to forget here and then yeah, come up with a combination in the final and cell state for this time step. So this operation, yeah, it's called selective forgetting. Okay, and then finally, yeah, selective. So this is the final output state for this time step, and this could be thought of as selective writing. And I think this HT is then finally yeah, used to come with that output. So the V matrix which we had in the RNN, so this HT is multiplied with that V and then we use that cross entropy loss to train the model. Right? Yeah. So in GRU, the only difference is we just have these two gates. There's no forget gate, and the way the forget gate is modeled is it's one minus the input gate. That is the only difference between. There are various ways of modeling this, but yeah, we just have so because of this, it has fewer number of parameters, and I think for some tasks GRU performs better than LSTM. It depends on the task. There's no explicit forget gate. So then we looked at the problem of vanishing gradient, how we could avoid this problem using LSTMs. Okay, so vanishing gradient issue was faced because we had this multiplicative chain and the gradient was getting after each multiplication we saw that the value of the gradient decreased. So something like a skip connection, okay, which we saw in ResNet, could solve this issue because uh, the gradient uh, the gradient could take this path and then uh, not bypass this multiplication step, which leads to this vanishing gradient. So you can see something similar is happening here as well when we look at the equation here. Okay, the cell state when you're computing, the current cell state ST is computed directly, like you're multiplying with this forget gate and then adding in. So this somehow gives that shortcut connection, and yeah, so this exact equation helps us to solve the issue of vanishing gradient. So exactly how mathematically it happens is given in the slides later, but yeah. So this equation here has that flavor of skip connection through which the gradients can flow in the later part of the network. Okay. Yeah. So to show that it solves the vanishing gradient, we just have to find one path through which the gradients can flow. Okay, through the network, and they. So this was the diagram. Okay, for the RNN, but for LSTM it will be more complicated. So it's this. Okay, and if you look at this path, okay, so we just want to find one path. If we consider this path over here, and if we see what the gradients are with respect to this, okay, you will find that the equation is finally what we get is this. Okay, so which is product of this Fi forget gate. Okay, now it could be that this Fi values are like less than 1, and then we'll again face this vanishing gradient issue, but because the model chose to forget these states, so this completely makes sense when we have very small gradients. So it's reasonable that gradients are small when the forget gate value is very small. Okay. And then similarly, we look at the exploding gradient, and there is this one path. It has the uh, same behavior like RNN. So again, we'll have this exploding gradient. To show that there is exploding gradient, we just need one path where we can say that that issue is still present there. So this is the path, and so this has similar behavior like RNN. So we'll have exploding gradient is not solved using this LSTM, but yeah, so we can use other, so it's easier to tackle the problem because we can use gradient clipping for that. So any questions or doubts regarding this? So this was what was covered in the lecture. Any questions? So what we'll do now is again go back to coding and yes, this code should be familiar to you by now because yeah, so we'll be using yeah same. So we'll have to define a model class. Okay, the training loop which is defined here. It's going to look very similar. The training loop as well, evaluation loop. Okay, the only differences we'll see for the data set. We'll look at the data set once. Okay, because we are dealing with text data here. So what we saw when training this BERT model over here in the previous example, we'll have to follow similar steps. Okay, so we'll have to take the text data, tokenize it, and then yeah, pass it to the model. And because it's a sequential data, sequences could be of different lengths, so we'll have to somehow pad them together so we can construct a batch and then pass it to the model, and then finally compute the score. Okay, so yeah. So let's see. Uh, so this is for reproducibility. So I'm setting the seed over here. Okay. So this dataset library from Hugging Face, it has all the, so we'll load the data directly from it. So this is the IMDb review data that we are going to look at today. Okay, so let's see what the task is. Okay, so this is how the dataset look like. Let's look at one review. So this is the review text for a movie, and there is a label for the sentiment of that. Yeah. So again, it's a binary classification task. Now, I don't remember what zero means over here. Okay, so this data set, if you look, it's not. So we'll have to shuffle it during because if you see, all the initial labels were zero, and then towards the end we have all the ones. I think one is positive. Okay, so this, let's read this and see. Look at the last one. Okay, so this looks like a positive review, right? So one means positive and zero means negative. Let's look at earlier reviews as well and see. Okay, so this is a negative review. So reading at the text, we can see zero is 0 is negative and 1 means positive. Okay. Yeah. So first thing is we'll have to tokenize the text. So we'll use this torch text library. Okay. And yeah, have this maximum length for tokenization. So we'll call this tokenizer. So this is the same thing that we did over here and dealing with text for training a BERT model. So here also, if you see, so we had created this dataset class. Okay. So we had read a pandas dataset and then created over here because we are down directly using, so loaded the data using this dataset class. We don't have to, so we'll get that in dataset format. Okay. Only thing that we have to do now is to tokenize it. Okay. And we'll be calling this map function, which is part of this dataset class. So it will tokenize all the text for us. So similar thing we had done here as well. So a class this, call this map class over here on the tokenization function. So you're doing the same thing over here. Okay. So this should tokenize the data. Yeah, so you have this text, the labels, and the tokens for that given class, and the length as well as recorded. Okay. So we'll split it into test and train, and here we are building the vocabulary for a data set. Okay, so this is going to be a paired token. So in a batch, when we have sequences of different sizes, we'll have to use this uh, paired token so that we can create a matrix and pass it through a GPU. Okay. Yeah, and this will convert the data set into integers, which is then, this is the same step that we did. Let's see the keys of this. Okay, so the IDs have the tokens for this given example. So here are all the IDs. So this is what we get after tokenization. Okay. Now each of this, so yeah, so as I said, different data points can have different size. So we'll need to pad all the tokens together when creating a batch. Okay. So this is a function called collator, which could be additionally passed to a data loader. Okay, so here is where we are creating a data loader. Okay, so what collate function does is, yeah, it does all this padding and gives us a matrix which we can then feed it through the model. Okay, so here is a function to create the data loader, and we'll be passing this collator function to pad and yeah, create a matrix out of all of it. So here we have created the data loader, and this is our LSTM class. Okay, so yeah, so we have this embedding because we have all the tokens. We'll have to pass it to the embedding layer. So there we have vector corresponding to each of those tokens, and then we'll pass those embeddings as input to the LSTM model. Okay, and these are some of the parameters. What should be the hidden dimension? How many layers should be there? So in the lecture, we did not look at the layer. We just saw one layer LSTM. Okay, so there could be multiple layers as well, and it could be bidirectional as well. Okay. yeah, so what happens over here is a different layer means the output that we get. Okay, so we'll compute the cell state and then we use that V to compute the output. That is again fed to a different uh, RNN. So there are two RNN stacked one after the other. So that is what is layers. And bidirectional means so we process the input from process the text from left to right. Okay, so we'll have one more in bidirectional LSTM. We'll have one more LSTM. We will process the input from right to left, and the final output would be concatenation of these two output of these two uh, RNNs. So that is bidirectional. Okay. Yeah. So this is the forward pass. Okay. So we'll pass the IDs through the embeddings. Okay. Yeah. So we'll pack all the sequences and then pass it through LSTM. Okay. Add this data part and then finally pass it through a fully connected layer to get the prediction score. Okay. So here are the parameters. Okay. Of the LSTM. So I've taken hidden size as 300, embedding dimension is again 300. So these two are same. Okay. Output would be unique labels. So yeah, in our case, it's just a binary classification. Okay, so number of layers is 2, and we'll be using bidirectional LSTM. Again, drop out a set to this. And here we have defined our model. Okay, so our model has these many parameters, and yeah, we'll be using yeah. So this Xavier initialization for linear layers, and yeah. So these are the initialization, how to initialize the weights of the model. So we'll apply that. Okay. Additionally, what we could do is we could also, yeah. So to get a warm start, what we could do is we could have used glove embeddings to initialize the embeddings of this LSTM. So these embeddings could be initialized using glove model, but then what we'll have to do is we'll have to somehow make sure that the mapping is correct of the tokens. So we'll have to, so if we are going to use this glove embeddings, we'll have to use the same tokenization which was used over here. Okay, so we cannot have our own mapping because so one way to yeah, this use initializing, it has been observed that using this glove embeddings, the training happens like converges faster and get better results. And same as before, so now we have defined a model. We have the data loader also. So next, what we have to do is yeah, fix the optimizer. So we'll be using Adam optimizer and the loss function, and then yeah, define the training group. So we'll go through the data loader, get a batch, okay, get the predictions from the model, uh, yeah, compute the loss, and do this backward pass, and this does the optimization step. And we'll do this for a bunch of time. And the evaluation code is again going to be going to look the same, but we don't want to track the computational graph when doing this. So we have put everything inside toss.node. Okay, and this is the accuracy that we are going to compute. Okay. Yeah, I'll not run this code. It is very familiar, and yeah. So finally, what we observe is the loss is decreasing. Okay, accuracy is increasing, and we're able to achieve around 90, 87 or something on this data set. Okay, and here are a few examples how the model performs. So if you can see, this is a terrible movie, so it has predicted the label 0, which is negative with 95% probability. Same as this is a great film, yeah, it predicts it as a label 1. Similarly, yeah. So the model is performing well. Here it's between this film is not great, it's terrible. Here it gets confused. Okay. So any questions regarding, so yeah. So we saw how to, so this pipeline is going to look similar to other models that we trained in the previous sessions. The only difference is the class that we are defined, and because we are dealing with textual data, we'll have to tokenize it and uh, pad different sequences together so that so we can create a batch and do a forward pass to the model. So any questions regarding this? So I'll be sharing this notebook, yeah, on my Google Drive. You can run all the code yourself and also experiment how you could, yeah, do better. So yeah, so I've used glove embeddings. You could use Word2Vec or something else and see how that behaves, and also see what happens if you train it from the scratch. Train the word embeddings from scratch and how that how what performance you get with that. So any questions? Fine, then yeah, let's I will end our session here then. Thank you for attending. I'll see you next week. Bye bye.